Well, hello, my awesome IB2 students. So today we're going to be doing a little bit more with continuous one-sided limits, looking at some really funky looking ones, okay? So the first thing I want you to do is I want you to try this warm-up problem that's right up here at the top. It says limit as x approaches 0 of 2x divided by x squared plus 4x. All right, so you're going to want to pause your video right now. And as soon as you're done with it, turn it back on because I'm going to go right into working our problem. All right, so if you're working this problem, first thing you want to do is if you try and substitute, which is always what you want to try first, you end up with an undefined function. You got 0 over 0, and that's not 1. So if you look down at the bottom, you can factor an x out. And then you can cross that x out with the numerator, so you now have 2x plus 4. Now, once you've done some algebra to it, now you want to try substituting in again. So you have 2 over 4, which comes out to be 1/2. So that's how you want to do that algebraically. Now, let's talk about each of these functions down here. So the first thing I did is I went in and graphed, and we're going to do that together. I actually drew a sketch on my graph here on the paper, but I'd like it if you were actually able to do the graph. So you're going to hit clear, and you're going to type in tangent of x. And if your graph is like you've been playing around with a window, like I've been playing around with a window, so I really can't see much of the graph, I'm going to say zoom, well, as soon as it finishes. Zoom 6. That always takes you back to a 10 by 10 window. Now, if you remember from pre-calculus last year, what you're seeing is a tangent graph with asymptotes. And those asymptotes are happening anywhere the function's undefined. So since tangent is sine over cosine, it's going to be anywhere on the unit circle where cosine's undefined. So let's take a look at the picture I have here. And that happens at every multiple of pi over 2, happening at a pi interval. So it's 1 pi over 2, it's not happening at 2 pi over 2, and then 3 pi over 2. So basically what's happening is if you're talking about your interval of continuity, these graphs are going to be discontinuous everywhere you have pi over 2 plus some multiple of pi. So that is where it is discontinuous. I'm just going to write discontinuous right up there. So that's where that is happening. So anytime you have x equal to that expression, you're going to have discontinuity. So where are you continuous? Everywhere else in that interval. So between negative pi over 2 to pi over 2, to pi over 2 to 3 pi over 2, you're continuous. Now, what kind of a discontinuity is this? Well, since it's not a whole, and it's clear that, let's just take pi over 2, for example. On the left-hand side, you're going to positive infinity. On the right-hand side, you're going to negative infinity. This type of continuity is not a removable discontinuity. It is a non-removable. Because it's not a hole, it's actually a break in the graph. Let's go take a look at the second one. So the second graph, the equation I'm going to put in is just this. I will not put in that part of the equation. Okay, so let's see here. I have sine 1 divided by x, and I'm going to hit close that parenthesis, and I'm going to hit graph. Okay, now if you're looking at mine, you're saying that's not what that looks like. I zoomed in so I could see a little better what was going on. And if you zoom in even further, you'll see that there's a zigzag happening. So let's zoom in a little bit tighter. Now you may be saying to yourself, that looks like it's perfectly filled in, but when I go and I look at the table, you'll see there's an error message at 0 telling you that you have a hole there. But the nice thing is that this fills in the hole. So we can actually say that this graph is continuous from negative infinity to positive infinity. Now, what if you like using a different type of notation? You don't like the interval, you like the set notation? That's perfectly fine too. So you could say for all real numbers. I could say that too. All right, now let's go take a look at the next one. That kind of looks a little bit like a werewolf or vampire teeth. Now remember, I've kind of got my calculator got a little weird there. I got the window setting a little odd. So let's take a look at the graph. Okay, so that's actually a pretty good picture of what's going on. Now, if I were to ask you about this graph as is right now, if you didn't have that equals 0 there, if you go in and you look at your table, you see you have an error message, okay? So what that tells me is that there's actually a hole in the graph, but this little piece right here fills in the hole, which is why I'm able to say that it's continuous everywhere, or I can say all real numbers. So everywhere it's going to be continuous. All right, so describe the interval in which it's continuous. We kind of talked about those. Identify any discontinuities. In both of these cases, we don't really have a discontinuity. It might have been called a removable, but then this little piece right here filled in the hole. So it doesn't have a removable discontinuity. Now let's go down to our last two. So I'm going to start with this one. So on this one, I can describe my discontinuity because a chunk has been taken out of my graph. It's called removable. And if we think about our definition of continuity, the limit for this graph is 3, but the value of the function at f of negative 3 is actually 4. So it is discontinuous and it's removable. It says find the limit of x as it approaches that point on both the sides. So let's see, so the limit of the function, we'll just call it f of x. If you'd like to pick a different letter, you can. As x approaches negative 3 is equal to positive 3 because that's the y value. Okay, but the value of the function at negative 3 is equal to 4, and those are not the same. Which is why it's discontinuous. All right, now let's go over and look at this one. Now this is a break or a gap in your function, which means this is a non-removable discontinuity. So on this one, I'm going to have to take the limit from the left and the right since things don't approach the same value. So as x approaches, looks like all the excitement happens at negative 1 from the left side of our function. I get a y value of 2. As I approach the limit from the right side at negative 1 of the function, I get 0. And these don't match. So that means you actually have a break in your function, so you can't even say it's continuous. So these are just some more visual examples to try and help you out a little bit. Your homework tonight is in the book. It's on page 79. I promised it was going to be a nice short bit of notes, and it is. I have graded your quizzes. I'll be returning them to you tomorrow. Remember that if you make a grade below an 80, you are welcome to retake it. But I will also remind you that just as I've done in the past, if you do better on your test than you do on the quiz, I will take the test grade and put it in. Because I know that this is very much, even though we're calling quizzes summative assignments, they really are a formative little check for you to see how you're doing. And sometimes you make mistakes that you wouldn't have normally made, okay? All right, so that's all my notes for today. I'm gonna upload this for you guys, for you to take a look at. If you have things that you have questions about, remember we can set up some time if you want to during the enrichment class period. We can set it up during your regular class period. You just gotta let me know you need some help. Don't sit there and let yourself drown, okay? But nice job on your quizzes.